Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into Apache Spark, the powerhouse behind modern big data analytics. Spark isn't just fast, it's a unified engine that handles batch processing, real-time streaming, machine learning, and interactive queries all under one roof. Its in-memory computing model makes it up to 100 times faster than traditional MapReduce frameworks. So why choose Spark? First, speed. Spark's in-memory processing drastically reduces I/O bottlenecks. Second, ease of use with high-level APIs in Scala, Python, Java, and R. Third, it's unified, no need for separate systems for batch, streaming, or machine learning. And finally, it's fault-tolerant, using lineage graphs to recover from failures. Let's explore Spark's core abstractions. RDD, or Resilient Distributed Datasets, are the foundational data structure, immutable and partitioned. DataFrames add structured schemas, making data manipulation easier. Datasets combine the best of both worlds with strong typing. Remember, transformations are lazy, actions trigger execution. Spark's architecture centers around a driver program that orchestrates tasks. The Spark context is the entry point, communicating with a cluster manager like Yarn or Kubernetes. Executors on worker nodes perform the actual computation and store data in memory or disk. RDDs are the core building block of Spark. They're immutable, partition collections that can be operated on in parallel. Fault tolerance is achieved through lineage graphs, which track transformations. RDDs support lazy valuation, meaning operations are only executed when an action is called. DataFrames provide a structured interface with schema enforcement, making them ideal for SQL-like operations. Datasets extend DataFrames with compile-time type safety. Spark's Catalyst Optimizer transforms and optimizes queries, while Tungsten handles efficient memory and CPU usage. Spark breaks down applications into jobs, stages, and tasks. The DAG scheduler creates an execution plan based on dependencies, and the task scheduler dispatches tasks to executors. Lazy evaluation ensures optimal execution by delaying computation until necessary. Spark SQL unifies structured data processing with SQL queries, data frames, and datasets. At its core is the Catalyst Optimizer, which uses rule-based and cost-based optimization to generate efficient execution plans. It supports pluggable data sources like Parquet, JSON, and JDBC. Spark streaming processes real-time data using microbatches, while structured streaming offers a higher-level, declarative API. It supports event-time processing and integrates seamlessly with Kafka, Flume, and Kinesis, making it ideal for real-time analytics. MLlib brings scalable machine learning to Spark. It includes algorithms for classification, regression, clustering, and collaborative filtering. With ML pipelines, feature extraction, and tight integration with DataFrames, building and deploying ML models becomes seamless. GraphX extends Spark with a graph parallel abstraction. It supports graph construction, modification, and parallel graph algorithms using the Progel API. GraphX integrates with RDDs and is perfect for social network analysis, recommendation engines, and fraud detection. Compared to Hadoop MapReduce, Spark is significantly faster due to in-memory computation. While MapReduce writes intermediate results to disk, Spark keeps data in memory. Spark also supports streaming and interactive queries, which MapReduce cannot do efficiently. While both Spark and Flink handle streaming, Flink excels in true event-time processing with lower latency. Spark, however, has stronger batch and machine learning capabilities and a more mature ecosystem. Choose based on your workload priorities. To get the most out of Spark, optimize partitioning to balance load, cache frequently accessed data, use broadcast variables for shared read-only data, and tune serialization formats like Cryo for better performance. Spark's memory management is handled by the Unified Memory Manager, which dynamically allocates memory between execution and storage. When memory is full, data spills to disk. Proper tuning of garbage collection can also boost performance. Spark supports multiple deployment modes. Local mode is great for development. Standalone mode uses Spark's own cluster manager. Yarn integrates with Hadoop, and Kubernetes enables containerized deployments for modern cloud environments. Running Spark on Kubernetes brings container-native orchestration, dynamic scaling, and portability across environments. Spark's native Kubernetes support allows executors to be launched as pods, enabling seamless integration with modern cloud-native workflows. Let's look at a real-world example: fraud detection. Spark Streaming ingests real-time transactions, while MLlib runs anomaly detection models. The system scales to millions of events per second, flagging suspicious activity with low latency. Spark excels in ETL pipelines. It ingests data from diverse sources like Kafka, S3, and databases, transforms it using powerful DataFrame APIs, and loads it into data warehouses or lakes. Its fault tolerance ensures reliability at scale. Spark enables interactive analytics with sub-second query responses. It integrates with BI tools like Tableau and Power BI, caches frequently accessed datasets, and supports both SQL and Python for flexible querying. Cloud platforms like AWS EMR, Azure HD Insight, and Google Dataproc make Spark deployment effortless. Databricks offers a managed Spark environment with collaborative notebooks. Serverless options and auto-scaling clusters further simplify operations. Databricks enhances Spark with a unified analytics platform. It provides collaborative notebooks, auto-managed clusters, and Delta Lake for reliable data lakes. It's widely adopted in enterprises for its ease of use and scalability. The Spark ecosystem includes core modules like Spark SQL, Streaming, MLlib, and GraphX. Add-ons like Delta Lake provide ACID transactions, while Koalas brings Pandas-like APIs. Integrations with Kafka, Hadoop, and Kubernetes expand its capabilities. Monitoring Spark jobs is crucial for performance tuning. The Spark UI provides real-time insights into job execution. Metrics can be exported via JMX or Ganglia. Logs and profiling tools help identify bottlenecks and optimize workloads. Spark offers robust security features including authentication, encryption, and role-based access control. It integrates with Kerberos for enterprise-grade security and supports encryption both in transit and at rest for sensitive data. Common pitfalls include excessive shuffles, poorly sized partitions, and inefficient caching. Best practices include using broadcast joins for small datasets, optimizing partitioning, and caching only necessary data to reduce memory pressure. Spark continues to evolve. Version 3.x introduced adaptive query execution and a vectorized Parquet reader. Project Hydrogen aims to unify streaming and batch. The roadmap focuses on performance, usability, and cloud-native deployments. To master Spark, start with the official documentation. Databricks Academy offers free training. Platforms like Coursera and Udemy have in-depth courses. Engage with the community via forums and Slack channels for tips and support. Spark has a vibrant open-source community with contributions from companies like Databricks, Microsoft, and IBM. A rich ecosystem of plugins and tools extends its functionality. Conferences like Spark Summit foster innovation and networking. Let's look at a classic example: word count. We initialize a Spark context, load a text file as an RDD, apply transformations like flat map and map, and finally use reduce by key to count occurrences. This demonstrates Spark's core concepts in action. Using DataFrames, we load a CSV file, apply SQL-like operations such as filtering and grouping, use built-in functions for transformations, and display results. DataFrames make complex operations simple and readable. In streaming, we read data from a socket, apply transformations like filtering or aggregation, and write results to a console sink. The streaming query runs continuously, processing data as it arrives in real time. Benchmarks show Spark outperforming Hadoop in batch processing by up to 100x. In streaming, Spark's micro-batch model is competitive, but Flink edges out in latency. Caching and in-memory computation are key to Spark's speed advantage. Use Spark when you need to process large-scale data, perform real-time analytics, build machine learning pipelines, or run interactive queries. It's ideal for data engineers, scientists, and analysts working with big data. Spark may not be the best fit for small datasets, simple ETL jobs, ultra-low latency event processing, or environments with limited resources. For such cases, lighter tools like Pandas or Flink may be more appropriate. In summary, Apache Spark combines speed with a unified set of APIs for batch, streaming, and machine learning. Its in-memory processing model delivers unmatched performance. To get the most out of it, understand its architecture, optimize workloads, and leverage its ecosystem. Thanks for watching this deep dive into Apache Spark. If you found value in this tutorial, smash that like button, subscribe for more tech content, and let me know in the comments what's your favorite Spark feature or use case. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.